All right, so I want to briefly review function composition with you. We're going to start with two functions, f of x and g of x. And you can multiply them, divide them, add them, subtract them. And you have to pay attention to domain. Whenever you want to combine two functions in that way, the input has to make sense in both functions at the same time. We want to look today at a new way to join functions. You've seen it before, but not multiplication, addition, division, subtraction. And so it's called function composition. And so the symbol is f compose g of x. And this is not fog, that's the composition symbol. It's not an O, it's a little tiny O looking symbol. And what it means is you plug g of x into f. So here's the pattern. You take your x, the number x, you plug x into g, and then whatever g does to x, you plug that output back into f. And by the way, you can do this lots of different ways. Instead of f compose g, you might look at g compose f. This would be g of f of x. You could even compose a function with itself. You could look at f compose f of x, and this would be f of x. So that's the notation. I wanted to do a couple of examples with you just to make sure that we know how to do this, and then also to think about domain just a little bit. So let's see some examples. Nothing too elaborate. Hopefully you've seen this before. So let's think about f of x is x squared, and g of x is root x. And so I'm interested in, let's say, f compose g of x. And this is, we said it's f of g of x, no problem there. But now let's think about it. Okay, this actually means something. So what does f do? When you plug something into f, you square it. Whatever you plug into f, you square it. So this is really g of x all squared. Do you see? The f squares whatever you plug in, and you're plugging in g of x. Okay, fine. Then you say, well, but g of x, I know what that is. That's root x. So this is root x squared. Okay, fine. And so now let's go ahead and square the square root, and we just get x. So f compose g, the formula for that is just x. And this is where people tend to miss the subtlety of the domain. It's easy to say, oh, look, the domain, if f compose g of x is just x, the domain of the function x is everything. We just looked at what x looks like. It's a line. You're good to go. You can plug in whatever you want. So the domain should be all reals, right? Well, no, actually, it's not all reals. So what's the catch? The catch is, think with me, you're plugging x into first g, then f. And so I could spend some time thinking about really tracking the domain down. It's nice if you understand that, but I'm going to cut right to the chase. The minimal thing you need to realize is whenever you do function composition, before you cancel out any fractions and before you cancel out any radicals, look there for your domain. For example, right here, I didn't square this radical away, and I realized that even though I'm squaring it out, there is a radical hidden in this composition, and that radical tells me that the domain of the composition is not actually everything. The domain of f compose g is actually 0 to infinity. It's equal to the domain of this function in this specific case. Now let me give you another example. Let's look at example 2. Let's consider the function f of x equals 1 over x, and let's study what happens if we look at f compose f of x. Well, look, what does the outside f do? It says 1 over whatever you plug in, so this is 1 over f of x. So this is 1 over x. And now I'm going to go ahead and flip it and say, well, yeah, but that just flips up to x. And just like before in the previous example, if you look at the formula for the output, you would say, well, the domain is everything, but it isn't. When you want to check the domain of the composition, look at the unsimplified version before you flip fractions, before you cancel radicals, and you can say, oh, wait, there's still a fraction hidden in here. So here I've got to have 1 over x not equal to 0. Whoops, excuse me. well, that's never going to happen. 1 over x is never going to be 0. It can't be 0. That's fine. Hold on. I am, need to hide this. What's going on? Boom. Okay. So let me pause and back up. I'm all confused now. So look at the unsimplified version, okay? And look at all fractions. And you say, well, here's a fraction. This is the bottom of this bigger fraction. So 1 over x can't be 0. That's fine. That's not going to happen. 1 over x can never be 0. But there's a second fraction. This fraction means its denominator can't be 0. And so in particular, we realize, hey, x can't be 0. So the domain of f compose f is everything but 0. It's minus infinity to 0, union 0 to infinity. Let me walk you back through that again in case this is something you're struggling with. I need you to see that there are two fractions here. Here's the numerator of one and the denominator of the other. This big denominator, 1 over x, is never 0. It can't be 0. It's just not possible because the top is never 0. So a fraction a over b is 0 only when the top is 0. And so this fraction can't ever be 0 because the top is never 0. So there's one fraction where I have the top and the bottom. There's a second fraction. This itself is a fraction, and I want the bottom not to be 0. So I want x not to be 0, and that's what's driving our domain here. So the moral of the story is, when you want to take the domain of function composition, don't look at the output formula, look at the unsimplified version before you simplify radicals and fractions. All right, let me do just one more example with you of function composition. I'm going to ignore domain this time, and I want to look at, I don't know, let's say this. Let's say h of x equals the cosine of x squared plus 1. You'll be asked in the homework to write this h of x, find two functions f and g where you can view h as f compose g of x. And I want to show you how to do that. So just think about it with me. It looks like I'm plugging x squared plus 1 into cosine. And so I'm going to go ahead and try in my mind f of x is cosine of x, and g of x is x squared plus 1. And now check, do these functions fit this bill? Well, when I plug x squared plus 1 into cosine of x, I do indeed get h, and so I'm good to go. That's it. All right, so let's wrap this up. We're almost done. Thank you for your patience, and I hope this review is helpful for you. We'll talk about even and odd functions, and then quickly we'll just touch on transformations.